Hello and welcome everybody to Advent of Code 2022 day 11. Now, today's problem I have some kind of mixed feelings about. The first part of it, as you go through it, it seems relatively straightforward. It's kind of fun, it's not super complicated. It's a little bit wacky and it's kind of just a fun one to go through. I thought my solution for how I structured it is quite elegant and it works out quite nice, but then there's sort of a thing with part two where there's pretty much a mathematical trick that you just have to know to be able to solve the problem. I don't really think you'd. I think it'd be very difficult to work it out entirely from first principles unless you knew this trick. And yeah, so it's kind of my least favorite sort of type of programming problem that you can get, because it's like, well, if you just know this one kind of obscure mathematical quirk, then it'll work out well. Otherwise, it won't, which is a little bit, yeah, I don't know. It's kind of feels a little bit unfair. But and I actually, full disclosure, I had to go and look it up because I suspected there was some mathematical thing, which I'll get to why my suspicions were of that. But I had to go and look this up to figure out exactly how to do it. It ended up being a literal one line change in my algorithm, but it's the key that unlocked the whole thing. So anyway, let's get into the problem. So we have day 11, monkey in the middle. So we're going up the river. We're on our way, but you realize that your backpack is lighter than it was, and some of the stuff from your backpack has been stolen by a bunch of monkeys who are playing keep away with your items. And yeah, that's about it. This actually reminds me weirdly of a programming assignment that I had years ago in college, where my lecturer came up with this bizarre example where he wanted us to code some object-oriented model that was to model monkeys, and you had to do things with the monkeys. And then I just remembered the distinct phrase that if an error case ensued, you were supposed to catch the error case and throw an error called monkey trouble. That's anyway. A complete aside. Just kept reminding me of that as I did this problem. Okay, so your input to the puzzle is this thing here. So basically, you're given an initial state where you've got each monkey. We've got a list of the items that they hold. These values that are associated to the items are your worry level for what the monkey is going to be doing with your items. You've got an operation, which is basically, so the crux of this is that the monkeys have your items. They go through them one by one, sort of inspecting each item. And as they inspect each item, your worry level goes up by this mathematical amount. So if a monkey's holding item 79, the new worry level for that item is 79 times 19, becomes the new worry level. There's then a test thing. So once the monkey's inspected the item, it gets a new value, and then the monkey checks that value, the monkey doesn't check it. Anyway, you check the value. If it's divisible by the number that's listed here, in the case for the first monkey is 23, then he throws it to monkey number 2. If not, throws it to monkey number 3. So effectively, this just would go on forever in a loop continuously. So each monkey checks their items in a list one by one, and they throw to another monkey based on some maths that we do here. That's pretty much it for the setup of the problem. What we're told is that we want to basically figure out how many times a given monkey is inspecting each item for a set amount of rounds of this monkey throwing game. So effectively, if you were to step through this list of monkeys one by one and follow their items and then redistribute them, if you do that for every single monkey, that'll give you one round completed, and then you can do that multiple times over and over again. And we're trying to then keep a count of how many times each monkey has handled an item, basically. And then at the very end, our output is, where are we told our output is at the end, is a product. So you take the two monkeys. So here's a list. Here's an example. At the very end of 20 rounds here, we've got the amount of times the monkey inspected an item. You take the two highest ones and you multiply them together, and that gives you your answer. So it's pretty straightforward. I mean, like, reading through it, it feels like it's going to be kind of difficult, but it's actually not very hard to implement, the first part at least. So let's have a look at how I did it. I didn't read anything from a file. I thought that would just be a pain to do, so I hard coded it because it's only a very small list. Basically, I've got a hash here where I've got the index for each monkey. Each monkey has a list of their items that they're carrying, so it's initialized with what our input was. I have a count for the number of times they've inspected an item. I have then two operations, basically, which are just lambda functions defined here. So the first one is the worry operation, which is what you'll increase the worry amount by every time they look at an item. And then we've also got a test operation, which is once that value has been updated, you use this to look at the item and see where you should throw it. And that's it. This data structure pretty much is what does the whole thing. The actual code then that executes in the loop is really very, very simple. So I have a loop from 1 to 20 because we're told for the first part anyway that we just want to do this 20 times. I go through every single monkey, and then for each monkey I go through all of their items. I increment that monkey's inspection counter. I then remove an item from the monkey array. I call my worry operation on it. Now, there is a subtlety with this as well, is that you're told that while handling the items, when the monkey's finished looking at an item before they throw it, your worry about that item goes down in that you divide by 3, and that tells you, so you're 3 times less worried once a monkey is finished inspecting it before they've thrown it, and that is just reduces the value basically of each one. And then that gets thrown to another monkey. That's pretty much it. You do this 20 times in a row. Then at the very end here, this little bit of maths is just giving me all the amount of inspections sorted, and then I get the two top values and multiply them together. That's it. So it's pretty simple. And I think it took me not very long to code it. And it runs pretty fast. And that's it. Yeah. So part 1, okay, works pretty well. Now, for part 2, they mix it up, and effectively it's the exact same problem, but what they say is there's 2 changes that they make. They basically say that this is going to go on forever, or it's going to go on for ages, so you want to model 10,000 rounds instead of 20. So you're basically just going to take the same loop and run it 10,000 times. And now you should be starting to think, oh no, this can't be quite as simple. And they also say that your worry level can no longer be divided by 3. So what this does is it means that the worry level values start to increase in their size massively, and they start to do it really, really quickly, which means that dealing with the numbers becomes really, really slow. And effectively, if I take my part 1 code and try and run it, I have no idea how long it would actually take if I just left it running, because it just sits there forever and does nothing. So it's one of these, I don't know exactly what it is in terms of how long it would take, but I'm calling it a heat death of the universe type problem, where it's just going to run forever and won't finish. So this is where you basically kind of just need to know the trick to do it, which is a little bit annoying. And I will show you now what that trick is. So we've said we're no longer going to be doing this division by 3. And instead of running it 20 times, we're going to be running it 10,000 times. So the code is pretty much the exact same, with just two small tweaks. So obviously we've tweaked the amount of times we run it. It's up to 10,000 now. The only other change, and this is what the crux of the whole solution is down here, instead of dividing by 3, I now do a mod operation with this variable called the common divisor. And the common divisors, I have them up here. There's two different ones, one for my sample and one for my input, and they're pretty big numbers. Basically, what these values actually are each of these modulus operations. They're all prime numbers as it happens. So that should also be another clue that there's going to be some weird mathematical trick you have to do in here. All of these are prime numbers. So this, what I call in this common divisor variable, is the product of all of those prime numbers. So I've just hard coded it here because it's only 4 and 8 numbers or whatever. So you multiply them together and you get a new number out of it. And then when we do our operation here, we basically take the mod of this with the common divisor, and then that updates our item value, and then we're passing that into our comparisons, which are all of these. So our comparisons are effectively just other modulus operations with these prime numbers. So this does seem like magic, and it seems a bit arbitrary that this should work. The key is that we don't actually care about these item values. We just care that the logic of the comparisons holds true. So effectively what this does is, so when you do a modulus of, and this is a pretty large number, when you do a modulus of any number, the output will always be between 0 and 1 less than that number. So effectively what we do is we've compressed the size of our variables. So these products would grow massive really, really quickly. And that's why it takes so long. It's so slow, and doing the operations is a nightmare. So if you do this, what it does is it effectively scales the problem down to a more manageable size of number. But it does it in a way that is mathematically consistent, so that when you do these mod operations, you still get accurate results. It's kind of annoying, really. Like if you knew that was a thing, then great. If you didn't, you'd have to go and look it up. And yeah, that's about it. I can't really say much more about it. I don't want to get into the maths behind it because I myself don't 100% fully understand it. I think I kind of get it, but I don't want to go explaining exactly how it works because I'll probably just get it wrong. The details, my explanation would probably be a bit wrong. But yeah, there we go. So that's this one. A little bit disappointed, to be honest, because I found in the past with these problems, there hasn't been, or it's not super common that there's just a little mathematical trick you need to know. Kind of reminds me of the problems you find on Project Euler, which that's sort of the basis of those problems, is it's all about solving mathematical problems. So yeah, I mean, it's kind of interesting. I learned something new from doing it. I didn't really know that this was a thing. So yeah, don't really know what else to say about it. Hopefully tomorrow is less mathematical and maybe more of an abstract problem solving type thing. But anyway, I'm going to do it anyway. So yeah, I hope you guys enjoyed, and hope this helped anyone who was maybe stuck on this problem, or yeah, maybe my explanation has clicked something in your head that makes you fully understand it, because I still don't know if I fully understand it. Anyway, I'll see you guys tomorrow.